So today I'm going to talk about the problem that we experienced about 2 years ago with our data storage platform, the issues our users had, our users being researchers, quant researchers, and a trading system itself, the implementation and the solution space that we explored, and then show some comparative graphs demonstrating how our current system performs versus our existing previous data stores. So just a quick show of hands. Has anyone here used MongoDB? OK, a good few of you. I won't assume too much knowledge, but there'll be a bit of code. It's not hard. So the lawyers made me put this up. Please don't read it. It's legalese. No, do read it. That's what they told me to say. I'm not going to sell you anything, and anything I do say may or may not be true, essentially. So the problem. Financial data comes in all sorts of shapes and sizes. We have sort of low-frequency data. This is your once-a-day data. Say, I don't know, take the FTSE stock index, going back 30 years. That's about 10,000 rows of data. To gigabytes of data. Let's say you take a matrix, which is all the stocks in the FTSE going across your columns, 30 years of data again. That's now 10,000 by 10,000. To 1-minute data, you actually have prices ticking every minute, which might be a useful thing to do for a non-high-frequency strategy, but a fast strategy nonetheless. And then you've got tick data, what people are buying and selling in the market right now. And we have about 30 terabytes of that currently. It comes in at 100, 150,000 ticks a second. And then other people have even larger data sets. We do some options, and these things go into petabytes, as some of the other talks have touched on. So most of these data sources that we're dealing with are time-series-based. They fit nicely into Pandas. We can use NumPy in a vectorized way on them. And researchers like that. They can plot a price curve. They can see what it's doing. They can create derived data items on that, a price-earnings ratio, that sort of thing. But there are other data sources as well, things like news data. Things that are sort of strings, essentially, with sentiment. Is it good? Is it bad? Is this stock going up or down? And researchers want to play with that as well. Are there sources of alpha they can tap, which the current system that we've built doesn't cope with? And they might dream up something else. So we had this sort of problem space of different shapes with different shapes, different sizes, and users wanting to access it all the time. So our users are quant researchers predominantly. We've got a cluster of machines, 100 of these, each with 24 cores and 100 gigabytes of RAM. And they're data hungry. These machines are essentially cheap white boxes that want to suck some data in, do some regressions, do some computation, spit out a signal, and then trade the markets for profit and win, hopefully. Now, that's not a statement of success or failure, by the way. But these things are ingesting both new data and historical data. And we want our cluster to really be CPU-bound, to actually be churning through data quickly. And what we found 2 years ago was actually the cluster was less than 5% utilized. We couldn't get the data out of our databases quickly enough, and it was essentially idle. And then we have human computers. They speak and they moan. And they sat in IPython Notebook and PyDev, and they're running through their code, and the data takes more than a second to come back, and they scream at you. And why is the data taking this long? It's only 10,000 rows. It's less than a megabyte. What's going on? And finally, we have the trading system. And our compliance guys, they care that the data is correct. No one's tampered with it. A researcher doesn't have a red button that they press for buying and selling. We're a systematic company. The computer does all the trading. So we need some way of versioning and ensuring that the data is safe in our data store. And it cares it's performant as well. So this is an example of a real piece of data that I pulled back, some sort of US equities price data, going across 9,600 of them. It's 8,000 long. They've got some silly symbology there. And it's essentially 10,000 by 10,000 8-byte floats. Now this is 600 megabytes of data. And if you're going to transfer that across the network, that's 5 gigabits. So our existing data sources encompass relational databases, tick databases, flat files, HDF5 files, and caches. Now, the relational databases, everyone knows and loves, and they're great for kind of low-frequency data. They're great for joining. And invariably, the first thing you say is, what's my schema going to be? How am I going to normalize my data? And that's wonderful for writing one row at a time. But you suddenly say to your database, give me back 100,000 rows. Give me back 10 million rows. And it doesn't work. Oh, well, it does, but you sit there and you can have some lunch. The tick databases are great. They're nice column stores. They're fast. They generally compress stuff, and you move the computation to the data, like Ian was talking about this morning, talking about moving computation to the data. But what you end up doing is you end up paying a lot of money for your tick database. And you end up writing in some obscure language, which would be a graph query language, or something even worse. And I think some people like it, but once you've invested in a small set of a tick database and you suddenly realize you want to scale out your algorithm, you're investing in much more of these license costs. And your databases generally have lots of storage on them, not much CPU, and they're very different from the white box compute that you've got over here. And so it's not ideal. Flat files are great, and HDF5 files, so they map quite nicely to the Pandas workflow. The problem you've got there is auditing, and how do you manage them? Do you put some local storage with each of your compute boxes? Do you ship the HDF5 files over? How do you cope with people writing to it? So you might then build caches on top of all this, because it's all a bit slow. And you put a cache on, it goes really quite fast. But then you've got your standard 2 problems of computer science, naming things, cache invalidation, and off-by-1 errors. So, I mean, you don't want to have a cache. Well, invariably, you have a cache, but it goes wrong. And we had serious problems with caching. So, XKCD there. There are 14 competing standards. We've all got some great data stores over there. Can we build something that's better? Can we actually build one system that is both performant, safe, has scalability and throughput in terms of latency, and total world domination? Can we beat both a tick database and a relational database? And I think we can. So we had some goals. We wanted to be able to get 10 years of 1-minute data. That's about 3 million rows of data in less than a second. We wanted to be able to get all the history of once-a-day data for 200 future markets in less than a second. We wanted a single store for any data type, from once-a-day data to tick data. We wanted data versioning and audit, so like SVN for our data. So you have a version number 1 to infinite, and you can pick and choose, and you can see how the data's changed between it. And we wanted to reduce the sort of impedance mismatch between our vectorized NumPy world and the database which is storing our data. Because it shouldn't be that hard. You shouldn't need to explode your world into rows of SQL and then iterate on that to pull your data back. So now I'm going to talk about the implementation, what we built, what it looks like. So we chose MongoDB for this, and there are a few reasons for doing this. The main one was it was free. I could download it, didn't have to talk to DBA. I could run MongoD, dbpath, and the thing span up. And it kind of worked. But MongoDB deals with documents, and a document is a Python dictionary, essentially. You insert the dictionary, you pull it back. And there is little to no impedance mismatch there. We very keen, as I said before, to move the data to the computation rather than the other way around, because we had all these white boxes. And MongoDB gave us the additional feature of scale out. We can add more nodes if we could see they were getting hot, move the data around a bit, and it supports that out the box. The other thing is, if we're going to back a database, and my boss came to ask me, why did you choose MongoDB? It'd be nice to see there's a company that gives you support should we need to pay for it for compliance reasons. So this is what we built. This is a sort of standard setup. We probably over-provisioned at the outset, but we had 1 new servers. We took 5 of them, put a SSD in each. 500 gig was what we could get at the time, about a year ago. And we had 2.5 terabytes of storage there, replicated onto another set of machines. So MongoDB has some config servers, which tell you how the database is sharded and where it's stored. And then it's got some lightweight MongoS software switches that route your queries to the individual shards that contain your data. So our data is financial market data. It easily shards based on the market, the symbol, the instrument. So it fits quite nicely. And there's a little document. You hopefully can't read it, but it's got a little bit of data in it. So what did our API look like? Well, we kept the idea of libraries from once-a-day, end-of-day data, say, to 1-minute data, to user data. Joe Bloggs has some data they want to store. They've done some manipulation in Python, and they want to store it back so they can share it with another researcher. We also have metadata, symbology mappings, being able to query things by more than one name, the Bloomberg ticker or the Reuters code. So we had the concept of pluggable library types, which are just Python classes at the end of the day. This is what the API looks like for real. Like all good Mongo programs, we call it Mongoose. Construct a Mongoose on a particular instance of the store. You can list what libraries are available. You slice out the libraries, list what symbols are in it. Then it's just a key value store. You can write and read that. You can snapshot it, which is taking a point-in-time snapshot like ZFS or LVM, something like that, across the current version of the latest symbols. And you can list snapshots. Notice the read, you can give it a version number, and that will give you back a version. So what does the schema look like? Logically, it looks like this. You've got snapshots that point at symbols and versions, and then those symbols and versions point at chunks of data. And chunking the data is key to getting that performance that I was talking about earlier. What you really want to do, if you're trying to push data to a cluster, is keep it simple. Chunk the data, compress the data, and push it to the client as quickly as the client can consume it. And you can get some amazing results. So this is an example of one of our chunk documents. You have a symbol there, which is US data. There's a segment for that symbol, say 1989. It has a SHA, which is just a SHA of the data being stored in that document. And then we have LZ4 compressed timestamps and column data. Now, as Francesc said earlier in one of the other talks, LZ4 is brilliant. It can decompress data faster than you can memcopy it. And it gives us 10 to 15x on real financial data improvement in space efficiency. And you'll see how that actually turns into performance in some of the graphs at the end. Finally, these things have parent object pointers. So this chunk belongs to 3 parents in this case, which are versions. So if 1989 doesn't change over time, because 1989 is gone, every time you save the time series again, that chunk of data has the same SHA, which means you don't need to use any more space to save it. So you get built-in deduplication with this schema. Obviously, if there's a correction or something to a price in 1989, you end up with a new chunk for that. But you can choose your chunk granularity appropriately for performance versus space usage. So we then have a version document, which is a US data version 16. It too has a parent, which is a snapshot in this case. And because it's Mongo, you've got a metadata sub-document in there, which is just ISINs, Bloomberg tickers, any other bit of metadata you want to store about that symbol. So this is the schema. It's trivial. But it's really fast. I promise you. I'll show you in a sec. On the chunks collection, we have an index. And the index goes from symbol, parent, segment. And this is a sort of compound index. So to slice out the data for that particular version 16 of US data, you find out what the ID is on the top right there. You do a query saying US data, that parent object ID, and then give me 1990 to 2000. And the database will start streaming back to you the fields from those chunks that you want. In this case, the timestamps and column data that you can decompress and create your Pandas data frame. So the code for that looks a bit like this. This is storing anything that can be pickled in this schema. cpickle dump the data, compress it with LZ4, which is the slowest bit. We're optimized for read here. Then loop over your chunk size. In this case, we've picked 15 megabytes. And then slice out from the pickle data I to I+1 chunk, store it in a data field, Python dictionary there, and give it a segment number. These are just sort of zero-based counts rather than a year, but you could put a year in there, which is what we have for Pandas data. Finally, checksum the data, and then insert it into Mongo. And inserting into Mongo is that one line there, just do a collection update, give it a symbol, give it a SHA. If it already exists, we'll find that document that exists with that symbol and SHA. Set the segment data, and then add the parent to the parent set, so the ID from the version document into the parent set. If the document doesn't exist, then the upsert will make the document exist. And because there's a constraint on that SHA field, there's only actually one document that has the same symbol and SHA in that database. So that's writing data. Reading data is even easier. It's just 2 lines of code. String join. collection.find symbol and the parent version, sort it by the segment field, and then cpickle load the decompressed data. Now, it's really stupid, but it's fast, because you're not actually doing very much in Python here. No for loops or anything like that. It's all happening in C. Well, there's a for loop, implicit for loop there. You can make this faster in Python, but we didn't need to. To do the same thing with data frames, you're doing 2 records, storing the D type away somewhere, chunking as before, and then reading is joining the data, restoring the D type, and then a from string. You can do clever things by creating an index of your chunks, or coping with multi-index, pandas data frames, that sort of thing. But again, very, very simple implementation. So our tick store, for example, is 200 lines of code, and it is order of magnitudes faster than what we've bought. So here are some results. So this is a confusing graph, but I'll explain it. On this y-axis here, we've got time in milliseconds from 0 to 8 seconds. This is the latency, the time taken to do a data read from, in this case, once a day data. So these are 10,000 rows again, a few hundred kilobytes to a megabyte of data. And on the left-hand side is you have some flat files stored on NFS storage. And on the right-hand side, it's stored in Mongo. In general, it'll be hot in the database's memory, because it's not very much data. But the really awful thing you can see over here is even for, on this y-axis, number of rows returned by the database, even for 0 rows returned, you can end up with massive latencies. And that's because we're sort of hammering the NFS server, unfortunately. And you get some great performance if it happens to already be in your disk cache. But you have no control about that trade-off. And you just need someone to submit a massive batch job to your cluster and have the researchers using the exact same NFS mount for their data, and suddenly researchers are screaming that all the data is slow. So finally, the colors. I should explain the colors. We scaled it from 1 to 256 concurrent readers on our cluster reading the data off. So when it goes red there are lots of machines in Python contending for the same data, trying to read them from the cluster. Mongo gives a sort of consistent latency throughout. This is the same sort of picture with 1-minute data. Again, going from 0 to 256 clustered users, reading up to 5 million rows of data on both sides, and then just scatter plot, plotting how long the client had to wait for that data. So on the left-hand side, you can see, again, massive variation. The 1-minute data in this case, we couldn't get it quickly enough out of the tick database, so we cached it in HDF5 files first on a parallel file system, and that worked apart from, again, when it's not the disk cache of the clients. And you see this massive spread. And over here, nearly all the data was returned within 10 seconds. Over there, no hope. So up until this point, we decided that we would replace our existing data caches and data stores for low-frequency data, counting up to 1-minute data as low frequency with Mongo, and it worked great. We got the results we wanted. But then we thought, well, could we do the same thing with tick data? And so similar plot, 8 processors. So the server we're hitting in question is limited to 8 CPU cores by license purposes, so this seemed to be the fairest thing to do in this case. But what you can see is they perform kind of similarly. I mean, all the Mongo data kind of comes in mostly in 4 seconds. There are 5 outliers that took a bit longer. In both cases, the data was hot in memory. There was no I/O being generated on the servers. But our simple, stupid Mongo store is returning data maybe twice as fast as the tick store over there, and with better consistency, better clustering of those scatter plots. This is now expanding again to 256 jobs, tick data. And I just should state that the data set we're loading here is the E-mini S&P, which is a future on the Standard & Poor 500 index. And it's a very liquid future contract. It's the most liquid one that we track. And so there's a lot of data, but it will all fit in memory in a big box for a year, for 2013. And what you can see over here is that we didn't manage to get to 256 cluster nodes. The database didn't respond with too much data. But you can see this sort of this massive spread. And as you start hitting it with 256 jobs, the database puts you in a queue, essentially. Mongo, meanwhile, was kind of returning all the data within 10 seconds. 5 million rows for lots and lots and lots of clients concurrently. We're waiting 50 seconds there, up to 80 seconds on the same scale. So scatter plot's great because it shows you what sort of throughput you're getting for an individual consumer, how long it took me to get that data. My 5 million rows took 10 seconds. Well, we know that 256 of these are happening concurrently. What's the actual throughput of the system? And that's what this is showing. On the left-hand side, we've got millions of ticks per second, going from 0 to 250 million, same scale on both sides. And on the right-hand side is the number of contracts or symbols this thing is churning through. Again, it's the same limited set of trying to keep the working set to one that will fit in memory, which is actually a sensible use case for us. And what you can see is that as we double the number of workers from 2 to 8 to 16 to 32, the throughput of the Mongo system doubles. So we go from, 10 million ticks a second all the way up to 230 million ticks a second there. The other tick store sort of topped out at 9 million ticks a second, whatever load we threw at it. And then finally, I'm going to show you some graphs of the load on the boxes while they do this. So on the left-hand side, we've got the tick store, and on the right-hand side, we have the Mongo store. And we can see that, and I've highlighted when the number of tasks was 32, which is kind of where this graph here starts. And somewhere around 16, we saturate the number of CPUs that we're licensed for in this tick store. So it's about 8 cores. And there's a little bit of system I/O in red at the top. But what you can see is that at 16, you're saturating a gigabyte a second of data throughput. So the tick store is reading nicely from its column chunked data, converting it into floats, sort of pickling it and packing it over the network. And over in the Mongo land, we've got 2 replicas here. So we've got 100 megabytes times 2 for those 32 tasks. Now, it's worth noting that at 32 tasks in purple, we're pumping out 30 million ticks a second versus 9 million ticks a second. So we're actually getting 3 times the data rate with something like a fifth of the network throughput. And this thing sort of doubles at each stage. So in conclusion, we built a sort of data store to store data of any shape and size. We tried to reduce the impedance mismatch between Python and Pandas and the way we wanted to access our data in a vectorized fashion and the database. And we can get once-a-day data going back 30 years, 10,000 rows, in 4 milliseconds. If you have a sort of SQL Alchemy iterator on your Oracle database, it takes you maybe half a millisecond per row, and that's 2.2 seconds. It's not bad, but it's 500 times slower. And if you've got a compute cluster that wants the data, that's an extortionate amount of time to wait. Meanwhile, the database is busy, and you've got a cursor open. We can pull back tick data at 3.5 million rows a second in Python. That's completely unoptimized Python. In Java, we get 15 million rows a second, tick by tick, from the same data store. From our other tick store, we wait 15 to 40 seconds, sometimes longer, depending on who's using it. We can hit it with 256 concurrent users. We've tested all sorts of scenarios, from just randomly accessing all of the data across the cluster, and you can generate massive I/O weights, etc. But the database doesn't collapse. There's actually, in this graph here, there's no real load here being generated by Mongo. All Mongo is doing is an index lookup and then streaming you data. So it might be generating some I/O if it's not hot in memory, but Mongo is just a memory mapped file with an index on it. And it works brilliantly if what you want to do is stream chunks of compressed data back to clients. And we've, in addition to sort of reducing the network load, the LZ4 has no noticeable impact to the calculation. But you can, I would argue, given that the way researchers work today is with Python and Pandas very frequently, building a versioned Pandas data store is a useful and a very efficient way of distributing your data across your cluster. Any questions? So the gentleman over there has a use case whereby he's got 15 years worth of data, and you want to look at sort of 2 fields in it and potentially access it randomly or sequentially.
It's the same as yours, but you have to filter. Can you somehow filter by timestamps-based in your one?
Yes, absolutely.
Before pulling it to the client.
So can we filter by timestamps for pulling from the client? And yes, so we choose our segment size appropriately. So in the case of the schema over here, this particular implementation is sort of a brain-dead schema for anything that you can pickle. If it's actually a NumPy or Pandas data frame, then what you might do is you would store the columns individually here. You'd actually have a bid and ask. And then this chunk only applies to a particular date range. So you choose your chunk size. So in our case, we're targeting somewhere around 100,000 ticks. So we're charging about a megabyte compressed. So 8 megabytes uncompressed, a megabyte compressed, or 800K compressed documents. The end result is that we can just slice back the set of documents that correspond to the time range. So you can put little start and end fields on here, index on the start, and then just slice back what you want. But I mean, it's a lot of data fundamentally. So you can generate workloads where you just hit all the data randomly, which will saturate any I/O that you've got. But what we find is that the people that care about tick data, say execution guys who want to build high-frequency algorithms, they will probably either take a given market or subset of markets and run their algorithm across those markets all through time, or they'll pick a year, say 2013, and then look at an entire market. And because they're chopping their data set, this does allow you to do that relatively efficiently. That's a good question as well. So he's asking, for this schema, do we have to write a new chunk every time we get a new tick? Because that would clearly be insane if you've generated a megabyte of I/O 100,000 times a second. The answer is you could, but no. So the way most tick collection systems work is you have in-memory collectors that sit on hosts listening to your message bus, and they collect the ticks, often for a tick database, whether it's, say, KDB, 1 tick, whatever, in memory. And then you've got sort of batch jobs that take that memory and then squirt it down. So we do something similar. So we collect, say, 3 hours worth of data or 100,000 ticks or whatever. I mean, at the moment, we're sort of building out this tick store. And we've been playing with Apache Kafka to just sort of squirt the ticks into a log-structured file. But we don't really care too much about latency from the collection point of view. So that has scalability and persistence. So yes, we do aggregate before we create these chunks. For corrections, you can do clever things as well. But it's the great thing about this really is that changing the schema is essentially free. You could put a little version number v:1, v:2 on that dictionary, and you can have your client code cope with changes of schema. He asked, do we require a tick database for the streaming? No, we don't. So if you buy a tick database, generally, unless you're very lucky, they're not going to give you the collectors. So you write your own collectors, and then they interface with a tick database, and then the tick database comes with some analytics, et cetera, that allow you to run your algorithms against the tick data. So I think a lot of financial firms already have tick collectors. So instead of plugging them into the tick database, we're plumbing them into this. Does that answer your question? So we've excluded the tick database entirely. There's no tick. There's no other proprietary bit of kit here. It's all open. It's all using open source bits that we've cobbled together.
How long do you wait to freeze the information to be stored?
Depends on the frequency. So at the moment, we've got a couple of things in production at the moment. One which is putting sort of minute buckets into the Mongo database as it arrives. Because what you can decide to do, say, because creating databases and collections in Mongo is very cheap, is that you can, say, have quite high frequency, low latency ingestion of data, which isn't chunked very, very finely, and perhaps not as well suited for the high compression case of streaming stuff back to your cluster, but then have a batch job that takes that and compresses it down for long-term storage. So the system we're building at the moment is collecting the data, sticking it into Kafka, which is just a log structured file, say with 30 days of data in it, and then batch job sucking that into Mongo is what we're sort of building at the moment. But we also do collection into Mongo.
Question in the back.
Yeah,
Question back.
MongoDB has a MapReduce function built into it. Have you done anything with that? And if so, have you had any success with it? Or?
We haven't done much with MapReduce. So we're essentially using Mongo a little bit like a key value store with some extra fields here. Because we're compressing the data and sticking it in the document store, we're not really using it as anything more than a memory map file with some concurrency control on the front. The MapReduce functionality that I've used works quite well. They also have an aggregation framework where you can do the same thing but in C without having to write JavaScript. I tend to believe that we can use Mongo to scale out our data access such that we can shift the I/O across sufficient machines that we can saturate the cluster depending on what the compute to I/O trade-off is that we want to hit. But I don't really believe that the most efficient use of a database is to create all the computation for consumption by the database. I think you should be sort of pulling the data out and sending it through Hadoop or whatever it is you want to use. Yep. So how do we cope with balancing low latency requirements with this sort of bucketing terminology? And it's a problem, absolutely. If what you care about is to the microsecond or millisecond granularity, this isn't trying to address that. This is really trying to address the batch storage of those ticks. What we're finding with Kafka at the moment is actually the latency end-to-end is about a millisecond. We don't have a huge amount of stuff that's co-located. We have some stuff that's co-located with exchanges. So we're not massively latency sensitive for a lot of it. But I think for the cases where we are, the clients that are, those clients like the execution engines will subscribe directly to the bus. They'll be listening for the ticks as they come in. They won't be trying to get the ticks out of the tick database. So it's more than reasonable to have a 3-hour delay or more. I mean, and even given the target for this data is quant researchers, there are actually licensing reasons for not giving them live data, and they shouldn't need it fundamentally.
Yeah,
I see what you mean. So you're wondering whether if we create many more chunks in the database, do we get better or worse performance?
yeah.
I think, from what I've seen, is the big cost is in routing the query in the first place and actually getting the database to build the cursor and start giving you the data back. So whether we chunk by year or by day has not much effect. But it is definitely the case that if you can squeeze a big chunk of data into your bucket, then you'll actually get quite a lot of compression in. And you'll find that you can squeeze, I don't know, a month's worth of data into a single document. And that can be incredibly fast to read.
Okay, last question. What are your thoughts on columnar database like HBase or Cassandra?
I don't have much of an opinion on them. I mean, I think that's essentially what we've built, but using Mongo rather than Cassandra. I mean, I think it depends on how your researchers want to work, right? So we're not building the system for ourselves, really. We're building them for our users who are sort of from the MATLAB R world, now in Python, and they can think in a sort of vectorized way about pulling data back, sort of drawing graphs, creating some vectorized computation to produce some derived answers. And it works well for them, I believe, to pull back matrices of large data and deal with them in situ. So no, I think it's a complexity trade-off. To build this, we honestly didn't have to write more than about 400 lines of code. And it's faster than our existing systems that we paid millions for.
HBase is Cassandra is also.
Oh, sure, yeah. But there's a complexity trade-off as well. Yeah, you could build this in a weekend. Promise.
Thank you, James.